Okay, I think it's time. So, Jian, you want to say something, Jian?
Yeah, I just want to welcome all the people on the online. So welcome to all the person attending the 27th COCHE Seminar series. So the topic this time is the progress on physical sciences for early detection of cardiovascular disease. I will chair this seminar with Professor Raymond Chen, and yeah, I think we all know the style of this seminar, and the main objective is to exchange about the progress in different area. And this time there are 4 students, 2 from Professor Chen and 2 from my group. So I let Professor Chen to chair the 2 first talks, and I will chair the 2 others. Yeah, without further ado, Professor Chen, you can start.
Okay, thank you, Jian. So thank you for the coming to this 27 COCHE seminar series. Yes, as Jian said, the first 2 talks are from my students. I should say that these are works in progress, and so these are not final results. But then I would like them to present that, and then hopefully we can get some input from any of you. Okay, so the first talk is about Navier-Stokes equation. Navier-Stokes equation is the fundamental equation in fluid dynamics. And then we are using this to model the flow of the blood inside the vessel. So today we have Jian to talk about using some kind of a neural network to simulate this. Okay, so Han, you can start.
Yes, thanks for the introduction. Hello, everyone. So welcome to this COCHE Seminar talk. And so for my presentation, the topic is about the neural solvers for the Navier-Stokes equation in the deformable vessel. Just to say, we assume the vessel wall will contain some elasticity properties. So this work, so my name is Han Zhang. So and I did this work with Professor Raymond Chen and Professor Xueshen Tai. Okay, so basically it will contain 4 parts. We will talk about the background first, and we'll talk about the mathematical formulation, so say the Navier-Stokes equation in other form. And we will introduce our approach, the neural approach, and we will present our demo results, which is not the final version, but you can see it's very, I think it's very beautiful, okay. So for the background, you can, I think we all know that the FFR, which the complete name is fractional flow reverse. Yeah, and that's to say you will insert a vial contain some sensors into the vessel to measure the blood pressure, and with that result, with that pressure distribution, you can just do a simple calculation like the division here. And you have a metric to illustrate whether you can use this metric to help you to diagnose whether there is something like the stenosis or something like a plaque. Okay, but this intrusive technology is harmful to patient because it's intrusive. So later, like in 2016. A computed FFR, which is named like the quantitative flow ratio, which is measured by the imaging technologies, and it will you can use these imaging techniques to get something like initial speed for the blood flow, and reconstruct for blood geometry, and you use a Navier-Stokes equation to numerically compute for the blood pressure distribution, so that you can diagnose this. But the main shortcoming for this method is that they ignore the elasticity or the deformable properties of the vessel wall, so it may bring some error. So here, the main factor in our work is that we consider for the vessels deforming. So there are some like some open packages or open softwares that related to our work. For example, the Phoenix, which is open software for the finite element method in numerically solving the partial differential equations. And another one is the SimVascular, which is developed by a Stanford University lab, and is specific for the blood simulation. So we will talk about our mathematical formulation then. So in our mathematical formulation, we need to consider for like 4 problems. The first problem is how the fluid flow inside the lumen, and how the fluid will change the geometry of the whole vessel-like domain, and how this geometry will influence this fluid back, and how this geometry deform. That's the 4 problems we need to mainly consider about. So the first one, how the fluid flow. So we use a simple Navier-Stokes equation to describe the flow inside the lumen. So this Navier-Stokes equation is based, we all know that is based on the momentum conservation, right? So there are some parameters in this PDE system. The ρf is the density for the fluid, and the uf is the velocity for the fluid. Yeah. So the sigma f is a Cauchy tensor. It contains the pressure and the fluid flow. It made up of pressure and fluid flow. So we have this PDE systems to describe the fluid behaviors, and then how this domain deforms. So first we have the fluid speed distribution inside the lumen, and from that speed we can compute for a stress that the fluid will produce to the vessel wall on the interface of the fluid and the structure. So that's to say that's the stress continuity. That's to say the Cauchy stress tensor along the normal direction should be equal to the Cauchy stress tensor of the fluid in the normal direction. And for that, if we have that relation, we can convert the force to bring the force that the fluid produced to the solid part. And then how the domain deforms. So basically inside the lumen, we should assume that it to be harmonic. So we have the Laplacian equal to 0, and the at the interface, the deformation for the fluid and the solid domain, I mean the computational domain, should be the same, so that the space is continuous. And another thing is the velocity continuity. That's to say, at the boundary, at the interface for the fluid and the solid, their speed should be the same. And the speed is to say the speed for the structure movement and the speed for the flow should be the same at the interface. So that's another setting in our physical problem. So here is some of the parameters. Just now we have talked about the Cauchy stress tensor for the fluid, and here is what the Cauchy stress tensor are specifically. So it contains the pressure and the fluid velocity. Okay, so let's talk about our approach. Our approach is mainly based on the PIN framework. The PIN is named as a physics-informed neural network. Okay, that's to say, we first sample some coordinates inside our computational domain, which is in our case is time coordinate and the spatial coordinate. So it's x0 and t. So we input this x0 and t. We hope that's the equation. We hope to get a function for u, which is fluid speed. So as we discussed just now, this speed should satisfy this Navier-Stokes equation because it should be based on physical law, right? The physical law is inflected by the PDE here, so it should obey this equation. So here we so conventionally we use finite element to do this, but here we use a neural network to replace it. So we input the coordinate into a neural network. The neural network is a function, and it output a result. So the result is U. The U should satisfy our PDE. So how should we do this? We make our PDE a residual loss function, and we do a regression, something like that, or something like data fitting, something so that we can change the parameters in our network. In our case here is the NU. So we optimize for those parameters. So finally, our NU should satisfy this loss function, and that's to say this NU is just our U that is described in our Navier-Stokes equation. So this is the basic logic. So in our case, we have mainly two parts. One is the fluid speed, another one is the domain movement. So we use like two different modules for these two different problems. Yeah. So for the left, you can see here. For the left two equations, you can see here is solved for the fluid velocity, and for the right two equation systems, they solve for the movement, the domain movement. So we use this like NP and NU to represent our U and P in fluid equations, and use the DF or use the NS and use NS as our DS here, and the NF as our DF here to fit the PDE systems. So the PDE systems are converted into the residual loss function form. So we have some loss function for training. So that's the whole of the basic ideas for our neural solver. So the result looks like this. We did this simulation for like 30 milliseconds. The condition is like you impose a fluid at the speed of 100 centimeters per second at the inlet. The inlet is in the left-hand side, right? Okay, so the pressure, you can see the yellow indicates the high pressure, and if it's more yellow, then the pressure is higher. So you can see the fluid actually flow to the right. So the pressure actually, the peak pressure actually goes to the right continuously. So we use Adam optimizer here, and use a linear rate of 0.001, and yes, and we have some physical parameters here reported in the tag in the upper left. So we have density for the solid and the fluid, and the viscosity for the fluid, and the elasticity parameters, and the Young modulus, and the Portion ratio for the solid part. So that's all for this result. So that's all of my presentations. Thanks. So should you have any problems, please don't hesitate to ask. Thanks.
Okay, thank you, Han.
Yeah,
So, do we have any questions for Han? So Han, maybe you can actually elaborate more about, for example, how do you train the network? So what kind of input that you need for the training of the network? Yeah.
So for the training of the network, we input coordinates, because you can imagine that for a function, for example, in our case here is the U. For a function, we have coordinates, the space, the location, the X, Y, Z, so which is known as the spatial coordinate, and the time frame, which is the time coordinate, which is T here. So we input this X and T. We hope a function could give us a result. And in our neural approach, this function is just a neural network. We hope this neural network to give us a result. but not every neural network can give us such a result. This neural network must be trained to satisfy some condition, some physical condition, and this physical condition is described by these partial differential equations. So we optimize so that the neural network can give us a result that can fit this equation as much as possible.
So
Yes.
basically, now with the input, then you get the UF and the P, right? And then you try to, is it P or rho, right? So P, right? So up there,
P,
right?
yeah.
Yeah.
P, yeah.
So then you hope that the P and the UF will satisfy, will minimize this norm, whatever inside the norm, right?
Yeah.
Yeah. But then here, then you don't, you only have this term in the loss function, or you have many terms?
No. This is just a simple case so that we can understand. For the loss function I have in our model, we have this like 4 terms in total. But we plan to add more because the inside of the structure, they have some inner stress, right? So we need to add one more PDE to describe that part.
Okay, so for example, so let's look at the LS2 on the right. Okay.
Yeah.
So do you need the DS? The DS and DF are output, right? So but then you have the DS at x0. So that is not the output from the level, right? So this is some input, right?
The x0 means that it's done on the reference domain, which means if you do a computation, you maybe first have a reference configuration, and you have a deformed configuration. So this x0 means that your computation is done on the reference domain.
Okay, so this is still the output. So I'm trying to understand. Yeah. Do you need something? Do you need the ground truth? That's what I'm trying to ask you. So, do you need the ground truth of this PDE solution?
No, we don't have a ground. We don't require any ground truth because it's like a function approximation or like fitting. So what's to fit? If in a supervised learning we fit for the ground truth, but here we fit for the residual loss here.
Okay. Yeah. So that's the major difference, right? So you should emphasize that. So because you don't need the ground truth in the training, yeah.
Yeah. Okay. Yeah.
And another thing is maybe you go to 2 slides later. One slide more. Here, so you have the maybe you click you have the parameters, right?
Oh, okay, parameters. Okay.
Yeah. So in practice, how do you obtain these parameters? In real applications,
in real applications, I assume those parameters are given. So that's to say the physical property of those vessel wall and the fluid part should be given, should be known.
Can we really measure this? I'm not sure. Maybe someone can tell us. Yeah. So, yeah. And also, so here you do not have the refraction, right? So at least for this one.
Sorry, what do you mean by refraction?
So do you don't have so you have the absorbing boundary on the right, right? So then you don't the ray does not reflect back, right?
Yes.
So in practice, should we have? So is the boundary condition reasonable?
I think it's reasonable because from my related work, which is done by a professor from Italy, Cotoroli, they did something like the same. They use the same boundary conditions.
I see. So well, of course, for Cotoroli, he's using finite elements, right, to solve the PDE. So have you compared your result with them?
Haven't yet. Yeah.
Okay, so you should, right?
Yeah, I should.
Yeah. Okay. Okay, I finished. So I don't know if others have any questions for you. Any questions from the audience?
Yeah, I have one question.
Yes.
Yeah, as you know, the blood vessel is a multiple layer system. So
Yeah.
how you take into account this? So your basic assumption is that everything is elastic,
Yeah.
and because also depending on the different level of cardiovascular disease, the inner stress or internal stress is different.
Yeah.
How is it possible to say edit this internal stress in different layer? What is the possible strategy?
Yeah, in our future work, because you can see at this moment we have only one layer, so the stress in the layer is uniform. So here is this is our assumption at this stage. But in the future, we'll add more layers, maybe because I know that around the vessel, the different layers of the vessel wall is composited of different components. So they have different elasticity properties. They have different like the parameters, different Young parameters, different portion ratio, or some other complex physical property. Yes, of course. So in our later stage, our future work, we will take this into account so that it should be a more realistic system. Yes.
Yeah, because the one who has a cardiovascular disease, basically the blood vessel become harder, so stiffness become harder, and also once you have say initiation of the crack, the interruption of the tissue, you relax the internal stress, so that accelerates the accident.
Yeah, this is doable by adding more adding more PDEs.
Okay, I see. Thank you.
Yeah, thanks for this question.
Hello, I have a quick question for you.
Yeah, please.
So, yeah. Eventually, after those theoretical simulations done, how this can be verified experimentally? Do you have any suggestion how to design an experiment to verify this?
Actually, I have talked with a student from the BME that you recommended to me last time, and I think they have a real simulation, real experiment for the artificial vessel, right? And if I think for the verification, we can design a simple artificial vessel that so in that case the materials properties are known, so we can improve those parameters into our model and do a computation and get a result and compare with the pressure distribution in his artificial vessel.
Right, but that's again is from a computer simulation to physical simulation. When I say experiments, I'm talking about the in vivo verification on human subjects, for example.
For this part is actually somewhat complex, because even if you insert a vial inside the vessel, the vial itself will influence the pressure distribution. So maybe we can also consider that vial, the influence of that vial into our computation to see if it makes sense.
Well, I'm not sure we need to insert anything inside the vessel, but invisibly we can measure blood flow using ultrasound and pressure using pressure non-invisibly. I guess what I'm trying to ask is that which portion of the body, according to your understanding, can be used for in vivo experiments, which close to the simulation scenario?
I think this question is difficult for us to answer. So,
okay,
yeah.
Okay, that we'll discuss later.
I would suggest, for example, Han. So because the Italian group have been doing this using mathematics, right, method to solve this. blood vessel simulation for like 20 years. So they must have some kind of validation, right? Using
Yeah.
Right.
something, yeah. So maybe you check their webpage and see whether how they validate their result.
Yeah, of course. Yeah.
Yeah, we'll go ahead to do this approach, because if we ask a clinician, they don't have any much, opinion, because they don't understand mathematics. Yeah, I think I'll probably look at other people's work first. Thank you.
Okay, thanks. Yeah, thanks.
So, okay, any other questions?
Sorry, I have a small question.
Yeah.
Yeah.
Yeah, and I just wanted to know, have you compared your results with the classical finite element solution? For example, velocity or pressure profiles?
I haven't compared, but or compared with other methods. Yeah, I just implemented my my method.
Yeah, because you just show a visualization of velocity profile or pressure profiles, but maybe if you show them in detail, you will see differences.
Yeah, I know. Yeah,
Okay.
I should do that. Yeah.
Okay, thank you.
Yeah, thanks.
Okay, so do we have any other questions? Okay, if no, then it's also time for the next talk. Okay, so Han, you can stop sharing now.
Yeah, sure. Thanks for the question.
Thank you, Han.
Yeah.
So our next speaker is Jian, Canning Xu. So Canning, Jason,
Yeah.
you can share your screen.
Yeah, sure. Wait a sec. Let me share my screen and
Jason is going to talk about this retinal vessel segmentation. So basically, that means to do segmentation on this on the eyes. So so usually this retinal vessel are used for this diabetes diagnostic, but sometimes it can be also used for cardiovascular diseases. So okay, so Jason, you can start.
all right. Yeah, so I'm Jason and I'm supervised by Professor Raymond Chen, and this is one of the work we did before, which is a 3-stage time frame based algorithm for retinal vessel segmentation. So here's the outline of my my talk today. I'm gonna give you some introduction on the topic, and then I'll introduce the framework of our time frame based segmentation method, and introduce the results, and also like discuss the future work we plan to do in the future. So here you can see like these are images containing vessels, and in the vessels in both 2-dimensional or 3 dimension, they always have the shape of like branching tubular. So this is just a visualization, and like we wanted to do the segmentation of blood vessels. So here we can see the segmentation of blood vessels is it's very is a critical task in medical images, and it requires like accurate and reliable techniques to aid in diagnosis and treatment of like various medical conditions such as like diabetic retinopathy, and also like cardiovascular diseases, and also like cancer. So accurately identifying those blood vessels in 2D or 3D images is very challenging due to the complexity and diversity of the structure of the vessels. So so basically we need to like exhibit various branching patterns, like complex topologies, and also like varying thickness. And it is very important to provide a detailed representation of the branching patterns and the topologies in the image, which requires like developing techniques that can identify the branching points, and also like the junctions of the blood vessels, and distinguish them from other structures in the image. And then is detecting blood vessels of varying thickness. So basically this account for varying thickness throughout the vessel structure is also like a major challenge, and also like small collusions and incorrectly segment noise, and and also like control the minimum thickness of the vessel throughout the user-defined precision setting. So this is something like we always need to you know, like we need to input the value, like you know, this is kind of like user input. And then we also need to develop methods that can aid in diagnosis and treatment of like practical medical conditions instead of just doing this as an algorithm. So here's the vessels in fundus images. Like the fundus images are images of the inner surface of the eye, and that allows for visualizations of the retina and the blood vessels within it. The blood vessel segmentation in fundus images is a crucial step in automated analysis of these images, and it can aid in the diagnosis and monitoring of eye diseases, such as what we just talked about, like diabetic retinopathy, and also like macular degeneration and other diseases. And the retinal blood vessels are part of the microcirculation system. And so any like abnormalities in these vessels can indicate or be associated with several cardiovascular diseases, including like hypertension and also diabetes and also a stroke. So yeah, so basically accurate and reliable segmentation of these vessels is very crucial, and it's very important for identifying the biomarkers can indicate the presence or the progression of these diseases. Yeah, so yeah, basically like this is a visualization of normal retina and diabetic retinopathy. We can see there's a lot of lesions in the right-hand side. So here's our, I'm gonna start to introduce our approach. So this is a workflow of our method. So we have three main stages as shown in the below figure. The first stage here is what we call it pre-processing. What we did here is we get an input image. We like the input image is fundus image, which is have three channels, the RGB channels. So we only use a green channel of the image. And then we do the COCHE to like enhance the contrast of the image to make the vessels more clear, clearer, sorry. So we have the clearer image here, and then we use some morphological operations to only emphasize the structure of the vessels. And then we use some filtering techniques to do the vessel enhancement to make the vessels clear to see in the image. And then finally, like this is not a binary image, it's a grayscale image. So we then use a grayscale image as an input and apply the time frame based algorithm to get the final segmentation here. So this is the main workflow of our approach. So here is first stage. We're going to introduce a third stage in details separately. So firstly, we do the pre-processing. You can see here that this is a visualization of the RGB channels of the fundus image. You know, for the first one, for the first line here, so you can clearly see that in the gray channel, which is the second image here, it actually have a clearer like vessels. And we can basically see it clearer compared to the other two. So we use the green channel to be the input, and then we we use a sorry, I think am I showing the correct? Okay, yeah. Okay, so yeah, we have the and then we use a green channel to do the COCHE, which is a limited adaptive histogram equalization to enhance the contrast. So we can see like the density here, like the frequency or the count of the distribution of the pixels. We can see that it's actually the contrast is enhanced by doing the COCHE. So after do the pre-processing for this is a first part of the pre-processing, and then we do the morphological filter to the contrast enhanced image. So this step enhances the vessels and also removes the uneven illuminations in the image, including the optic disc and also the exudates. So here is the optic. I'm not sure if you can see my mouse actually.
Yeah, I can. We can.
Okay, so because of, yeah, like here, this is an optic disc, and this is you can see some small dots in the retinal image as well. So those are like kind of what we call exudates, and exudates is one of the diabetic retinopathy that caused by diabetes and also related to some CVDs. So yeah, so basically we take the vessels from the image. This is what we did for the pre-processing. And then the second stage is vessel enhancement. The reason why we want to do this is we want to emphasize the vascular structures, because the vascular structures is very crucial for enhancing the vessels and rendering them distinct for the segmentation. So we here we use an improved Frangi filter. So improved Frangi filter is actually also called like German filter. So the German filter is applied to enhance the vessels. And in German filter, we have one parameter, which is tau. So tau basically controls the number of it's kind of like a threshold. So it controls like the number of vessel pixels we can extract from the image. So if we have a if we have a higher tau, if we have a lower tau, we will have more vessel pixels like this, the B here. But also we will have a high level noise. And if we increase the tau from B to D, we can see the noise is actually restrained, and it also eliminate part of the vessels as well. So yeah, so basically we're gonna choose a higher tau because we don't want it to be too noisy. And then we use a D here as an example, and then we apply a denoiser called a small sort of variation to do the denoising. So the reason why we don't use any other simple techniques like median filter or like Gaussian filter is it do have a lot of parameters, and also the denoiser STV here can also preserve the edges as median filter did, but we do a better job. Yeah, so this is the reason why we use this. And another reason is after we use a German filter, we have a high level noise in the image, even though we can see the vessels clearer. Yeah, and then the third stage, which is the final stage of our approach, is the time frame based segmentation. So here you can see the three columns are showing the fundus images, the ground truth, and also the segmentation results. We can see that we actually get most of the vessels containing also those thin vessels quite well, even though we do ignore some of them. That would be part of our future work that we're gonna try to extract those small thin vessels as well. So the workflow of the time frame based segmentation is this is a method that Professor Chen proposed years ago, and in the original method, there's a threshold or a fixed threshold that we convert an image to apply the time frame algorithm to convert the image into a binary image gradually. So here we adapt an iterative time frame technique to segment retinal vessels, which we set you can see here is a Q. The Q is a quantile. It's a percentile of the we just set a percentile and set the threshold to be the Qth percentile of the distribution of the pixels, the intensity of the pixels. So to make it we just kind of reduce one of the parameters we need to set. So here we the first step is initialization, and then we gradually we firstly divide the pixels into boundary pixels and other pixels, and we gradually reduce the number of boundary pixels to make the image into a binary image here, which is a segmentation. And then here is our numerical results, and we apply the method on two publicly available data sets, the drive and the stare. And our approach performs competitively compared to other advanced approaches. We also compare like three supervised approach. You can see that actually for supervised and unsupervised approach, we kind of get quite also like all of them get quite good results. The supervised methods, they always use a lot of training points. So here our approach is unsupervised, so we don't need any training labels in the process. So we compare three metrics: the sensitivity, specificity, and also the accuracy, the over accuracy. So we get quite good results on these two data sets, even though there's still room for improvement. So for the future work, we're gonna implement the time frame based segmentation algorithm with local adaptive thresholds. This will be more this can be more flexible for those images with uneven distribution of illuminations. And then we also want to develop and refine techniques for accurate and reliable measurement of the vessel diameters. This can be quite important biomarkers for the diagnosis of CVDs and also diabetic retinopathy. And besides, we also want to combine unsupervised deep learning techniques such as the contrastive learning, and just use these techniques together to segment not only the vessels, not only the diabetic retinopathy, but also like cardiac images. And so this is my presentation today, and thanks for listening.
Okay, thank you, Jason. So don't know if the audience has any questions, but then let me start with a question. So why do you choose the green channel only? So you say that the green channel is look better than the other, but usually people will transform the phi channel into another, let's say the YIQ, and then use the Y, right? So the intensity to do it. So have you tried that?
So there's a lot of literatures on doing this. Like we can definitely choose some other techniques like dimensionality reduction to reduce.
Not dimension reduction. I mean, why do you just choose one channel in our
one channel? Oh, okay. So like you can see here, right? If you see the three channels of the images here, the red channel and the blue channel actually don't give us too much information.
Yeah, but then they may have independent information. So that's why I'm saying that you should transform them into other
color space.
So probably they will give you more information than just a green channel.
Yeah,
So have you
that's
tried others? So for example, this YQ or LAB or something like that. Have you tried that?
I think that's correct. So maybe we can try this. Like we do see some literatures on transfer the images into LAB, which is maybe nonlinear, and then to nonlinear color space, and then do the segmentation. Yeah, we should try that.
Yeah. Okay. So maybe I open it because your time is almost up. So anyone has any question? Any questions from the audience?
I just say thank you for your wonderful job. I wonder that for your next step, when you look at the fundus imaging, is there any possible way to predict the stroke or something like that? or it's too far?
I think a more like a closer step is we can try to we can try to measure the diameter of the vessels. So this could be quite useful for I think I didn't remember, but I think it is really related to some cardiovascular diseases. You know, the diameter of the vessels, if we can segment the vessels.
So yeah, are you in third year or fourth year? I forgot your status.
No, I'm second year. Yeah, I'm second year.
Second year, right?
Yeah.
So what's your plan eventually? You continue working on this fundus imaging, or you want to change modality of imaging?
Yeah, I think I'm not going to work on the fundus image a lot in the future. I will plan to like work on the cardiac images. Like we can segment the lesions of you know, some of lesions in the heart instead of in the eyes.
Yeah, I think that'd be wonderful. I know there's you know, public imaging at this moment that have you know, plugs, because one of our emphasized research is plug. So if you can you know, do those one, that would be much better. And also we are planning and to see whether we can have a 3D scanner. I have not really discussed with Raymond yet. We will discuss tomorrow. Okay. So I'm thinking that we can have our own equipment for those cardiac, so that you know, at this moment maybe have to use public database. Thank you.
Yeah. I also noticed the public data set on cardiac image.
Okay, thank you. Any other questions? Okay, if no, then I will hand the chairman to back to Professor Lu. Jian.
Okay, thank you, Raymond. So next speaker is Mr. Li Hongfu. He is a first year PhD student, so he joined CTU since 1st of September, 6 months ago. So his topic today is a lab on chip system in the surface enhanced Raman spectroscopy quantitative analysis. Yeah, Mr. Li, please.
Thank you. So so good afternoon, everybody. My name is Li Hongfu, and today I'll be sharing something on the quantitative analysis in surface enhanced Raman spectroscopy system coupled with the microfluidic implementation. So today's report will be generally divided in 3 different parts. And in the first part, I will introduce some basic background knowledge related to the SIRS detection, especially the detection of the cardiovascular disease, the prediction and the meaning of doing the quantitative analysis. The sample dilution and the pre-concentrations are the 2 essential parts of the quantitative analysis. So in the second part, I'm going to make a comprehensive introduction to the sample pre-treatment with the microfluidic chip. And finally, I'll also be talking about the outline of my project's technical routine and the problems that I'm going to try to optimize. And here we go straight to the mechanism of the SIRS detection first. To the best of my knowledge, 2 mechanisms are contributed to the surface enhanced Raman spectroscopy, as is shown on in the feature on the belowing. In the first case, A, the electromagnetic enhancement of the silver nanoparticles is the key to generating the amplified signals. And the SIRS hotspot is generated in the gap between the 2 close nanoparticles. And the other mechanism is related to the chemical issue. When the analyte is bounded on the nanoparticle substrate, the interaction on this bonding will have a direct impact on the electron transfer between the 2 substances, which will further amplify the signals that we get. So we implement the SIRS technology for detection. We are actually focusing on the specific molecular vibration generated by different substances. And the band position and the band shape are the 2 features that can act as the fingerprint of the certain substances. And that is also the foundation of our detection. And usually we got narrow bandwidths during the detection, and these narrow bandwidths also allowed more targets to be fitted into the spectra with the minimal crosstalk, which means it owns a high resolution and thus holds the possibility of the multiple target detection. More specifically, there have also been some existing studies that applicate the SIRS to cardiovascular disease detection. The biomarkers shown here are typically relevant to the cardiovascular disease, but so far, most of the studies or the applications on the basis of the SIRS detections are still conducting the qualitative analysis. Indeed, in most cases, the qualitative analysis is good enough to indicate the CVD, but however, if we do not care about the quantitative concentration of our target indicators, we might lose some important information generated from the interaction between the biomarkers, as is shown on this figure. What I want to say is that the single biomarker-based detection might not be that precise for the early prediction of the CVD disease, but if we can conduct the quantification, it provides the potential to reveal the value relevance connection between the biomarkers and the diseases, which can only be obtained from the experienced clinical doctors in the past. And the figures on the belowing shows a potential way to build a statistical model between the quantitative data and the disease, and a final mark could be obtained after the calculation of all the contribution for reference of the risk. And the calibration must be done in advance of the quantification. Here I show three basic methods utilized in the SIRS detection. The internal standard methods is commonly used in the correlate-based SIRS detection, but since the step to fabricate the internal standard metric can be costly and sophisticated, it is not the friendly case for general application. And the standard curve methods is the most commonly used methods and can work well with the aesthetic condition. It shows great advantages in efficiency, but due to its lack of the robustness, it wouldn't fit the complex matrix for the detection. And the standard addition methods takes the influence of the complexity into account and work under different situations. But its steps are also complicated, and sometimes it's not an easy case to find the standard matrix of the target molecule. And usually when we are conducting quantitative analysis, we should obtain a series of the SIRS curves under different sample concentration. And we extract the peaks as the feature of their concentration, and after some data processing, we get a curve of the scattering intensity versus the sample concentration. But it's also worth noting that this would be a very ideal case that all the target analyzed without the pretreatment process in one biosample can lie in the same linear dynamic range of our detection, which is the green zone in this figure. And there are also some factors that we need to concern about, because these factors would rather hamper the stability of the signals or weaken the original signals induced by the samples. Nanoparticle aggregation and burning effect and the saturation effects are the three major issues that we are concerning about when we conduct quantification. But hopefully, the microfluidic platforms offers a potential to greatly control most of the factors in the diagram. And here are the examples of the existing applications in SIRS detection. The first example validates the quantification of the uric acid in human urine. It demonstrates that the SIRS detection with the standard addition methods can even be comparable with the high-performance liquid chromatography. The research also validates the optimum concentration range to conduct the sample detection. For samples beyond this range, a dilution process will be needed. And in the second example, the scholars studied the man-made interference in the matrix. Cargo red here works as a target, and the methyl red works as an interference. And in their study, a microfluidic chip was used to precisely control the condition of the fluids to avoid the errors caused by the manual operations. And moreover, the volume of the fluids is strictly controlled to be the same within the different testing groups. And it is also interesting that the research group used more than one variable in this model to analyze the results. By contrast, a strategy of principal component regression is used to gain more reliability. And in other cases, the signals obtained from the simple matrix and the complex matrix are compared. And the NTX here stands for the target substance to be detected, which has nearly a perfect linear range of 2.5 to 10 micromolars, and a dynamic range extending up to 80 micromolar in pure water. And in the case of the human sample, the urine, the validation process still works well, and the calibration curve still shows great robustness in different samples respectively. However, it's worth noting that the choice of the bands and peaks for analysis can greatly affect the prediction quality. With the wrong selection of the bands and the peaks, the mean absolute percentage error sharply goes up to 144%, and compared to the normal level of that is 21.4%. So what I want to mention here is the challenges and the demands in quantification. As mentioned, one of the prerequisites for quantitative analysis is that the sample concentration should be relying on the linear dynamic range of the source detection. The typical linear dynamic range of the source detection is 1 to 100 nanograms per microliter. But due to the complexity of the biosamples, we couldn't ensure the feasibility without the pretreatment process. And so that's why we are calling for more effective dilution and pre-concentration methods, which can be integrated into the source detection. So let's see how the dilution is conducted in the microfluidic system first. Generally, these methods can be divided into two different categories: the volume mixture-based methods and the diffusion-based methods. The former one functions with the change of volume ratio of the sample and the buffer liquid, and is usually implemented in a static condition. And the later one functions with the change of the flow rate in the laminar flow condition and adjustments like the hydrodynamic resistance to change the dilution factor. And in our case, our target will be achieving the sample pre-dilution in either continuous or more intensive discrete conditions. And also, studies have shown that the responding curve between the intensity and the sample concentration could be either linear or logarithmic. So the compatibility should also be taken into consideration. Here are some existing applications. The first method demonstrates an idea of the programmable microfluidic chip. And the principle is to inject the diluent while draining the mixed samples of the same volume. And the scale of the droplet can be easily adjusted by changing the pressure of the fluid or the expanding time of the valve. And the mixing of the sample depends on three programmable valves. The diffusion process of the sample can be accelerated in this way. And the dilution ratio is highly related with the expanding time of the valves at the inlet. And the scholars have already proven the validation for generating logarithmic concentration. In this assay, the device is compared to a circuit, and thus the hydrodynamic resistance is compared to the resistance in the circuit. And by changing the channel structural index, the parameters, the dilution ratio can be modified precisely. And different combinations of the channel structures contribute to the flexibility of the diluting function. And that is to say, the chip can generate both the logarithmic and linear concentrations by simply utilizing different designs of the channel. And here are the basic methods for the pre-concentration in our microfluidic system, mainly the stacking methods, the gradient focusing methods, and the trapping methods. And these non-solvent removal methods can generally be achieved to conduct a more selective concentration process, because the methods shown here mostly require that the target particles for the concentration process is charged or could have a bonding effect with the substrate, like the immunocapture-based trapping. And many studies have shown that there is great compatibility to integrate these methods into the microfluidic system. And so in the next few slides, I would like to show some existing examples of the non-solvent removal methods coupled in microfluidic system. The first application is a job lab coupled platform, and this is a typical electrokinetic trapping methods. However, the fluids in the channel are not only driven by electro-osmotic flow, but also controlled by the pumps connected to the upper channel. And when the trapping zone or the concentrated zone is fully prepared, a pulse will be applied in this syringe and squeezing a certain amount of the liquid out of the channel and forming a droplet in the channel on the right. By adjusting the magnitude of the pulse, volume of the droplet can also be controlled precisely, making it also flexible and amiable for the next step detection. And these two cases are still applications using the electrokinetic trapping methods. Figures on the left indicates a special design that utilizes a negatively charged valve to replace the original nanochannel in a typical design form. The concentration factors can achieve 1,000 times in 2 minutes, while the figure on the right is another design. So we basically know that the electrokinetic trapping methods needs a nanochannel or a nano array to create the enrichment and the depletion zone, and the porous materials such as hydrogel can perfectly offer this condition. So in this section, we talk about other form of the pre-concentration, the solvent removal methods, specifically an effective way for general concentration of all the samples components in a microfluidic platform is the evaporation methods. The existing applications indicate three major branches in this topic: the direct evaporation in an ambient or the closed environment, the membrane-assisted evaporation, and the droplet shrinkage methods. And among these methods, the direct evaporation methods holds the greatest simplicity and the repeatability in the same ambient condition. Other methods somehow suffer from the complicated and delicate structures like the membrane layer and wouldn't fit for a situation that requires multiple steps in concentration. However, evaporation efficiency was still the biggest challenge for a practical application. The evaporation flux still remains to be like a few nanoliters per second, and it usually takes more than an hour for the whole pre-concentration process. And I'm trying to find a way for the improvement of the efficiency for this technical, while reserving its original simplicity for the practical application. So in this part, I'll give a brief introduction to the mechanism of the evaporation and show some tentative solutions for the channels in different scales. So water potential, there is a unit to describe the tendency of the water flux during the evaporation. Generally, the water transport from the position with higher water potential to where with the lower one. And in a liquid environment, it is determined by factors like the capillary force, the solution concentration, the hydrostatic pressure, and even the gravity. Well, in the vapor phase, the water potential is calculated from the relative humidity in the air, which results from the partial vapor pressure and the saturated vapor pressure in the air. So in this session, I'll talk about the other, and this is an example to illustrate this tendency. Due to the curvature difference of the meniscus radius, the reservoir 2 has higher water potential compared to the reservoir 1, so the water in the channel automatically transport from the right side to the left side. Also, we can consider both the reservoirs have higher water potential compared to the ambient air, so there will also be a evaporation process from the liquid phase to the vapor phase. And the equation here shows a typical model of the evaporation process at the interface between the liquid phase and the vapor phase. The direct driving force of the evaporation is generated from the water potential difference between the gas and liquid interface and the ambient air, which is also relative to the concentration of the liquid. and the relative humidity in the air, and the thickness of the boundary layer. So if we consider the whole process of the liquid flow in the channel, the hydrostatic pressure drop during the flow should be taken into account. And interestingly, due to the scaling law, the impact of the pressure drop plays different roles in different scales. In the microchannel, the resistance effect can nearly be neglected, and the evaporation is dominantly limited by the ambient conditions. But in the nanoscale, the evaporation rate is comparatively high if there wasn't any constraints on the channel. In other words, if we want to accelerate the evaporating rate in micro or nano channel, and such a based microfluidic chip, we should either improve the ambient conditions or the initial condition of the channel, since it's the dominant region that affect the evaporation directly. You can further make some comparison to the circuit system. If we reduce the dominant resistance in the circuits, the current in the system should be greatly increased. And this is such a similar case if we want to increase the larger flux in the microfluidic system, the evaporation rate. And here I listed some prospective solutions for both micro and nano channel, such as reducing the relative humidity in the air or the thickness of the boundary layer using the convection flow and things like that. And there are also some like universal strategies, like using the additional power supply to obtain higher delta phi, which is the change amount of the water potential, and the fine control of the delicate balance between the two.
You need probably to conclude quickly, because you exceed the whole time, including the question time. Okay.
Right. So that is the conclusion. And this is also the last part. I'd like to illustrate the outline of my project again. The final objective of my project is to conduct a quantitative analysis in CVD samples using the SIRS technology, since the quantification shows the potential to reveal the interaction between the multiple components in the sample, which the qualitative analysis is indeed hard to do so. However, there are some restrictions in SIRS detection, like the narrow linear dynamic range for sample detection. So we want the self-adapted dilution or the pre-concentration process before the detection. So specifically, the non-solvent removal and the solvent removal pre-concentration methods result in more selective and more general concentration effect for the sample. And finally, an integration is supposed to be made to couple all the modules together in a likely like a platform that can adjust easily and generate different dilution or the pre-concentration conditions, including the dilution and concentration factors, and that's all.
Okay, thank you. We have time for 1 or 2 questions. So any question from audience?
Yeah, well, thank you for your wonderful job. It's a very exciting job. So I just wondered that have you any experiments done with CVD cell or CVD related material?
No, actually, I'm still doing the simulation job for the structural design, because I'm
right
now, yeah.
What's the plan on the direction?
I'm sorry?
What is your plan on the application side?
Application, I'm designing a platform that can integrate the dilution part and the pre-concentration part
right.
to treat the samples. And if possible, I would also like to do some data analysis based on the methods that I previously mentioned.
Right. I'm asking that you will need time to get a CVD patient sample. So my question is, do you have any plan? Because you needed to communicate with the hospital and to get that kind of sample. Do you have any plan for that? Yeah.
In our group, we do have some CVD samples, because I'm also under the supervision of Dr. Q. So Well, we are doing a collaboration, and we do get some CVD samples here, so there's no worry.
That's good. Okay, thank you.
Thank you.
Other question? So if not, let's move to the last talk today. So the next speaker is Miss Yang Qing. She's also a first-year student. Before joining the CTU in last September, she was a graduate from Shandong University with a master's degree. So today's talk is application of Raman spectroscopy in micro and nanoparticle analysis. Because before the CVD incident, we believe there's some micro and nanoparticle in the blood vessel. So if in urine or in other body fluid, so we try to develop a generic method so that we can detect very tiny particle for early detection of cardiovascular disease. So Ms. Yang, please.
Okay, thank you. Hello, everyone. The topic I want to introduce is the application of Raman spectroscopy in micro and nanoparticles analysis. And I will introduce it in these 4 parts. The first part is the background. And the environmental pollution is one of the significant international concerns today. There are various emerging pollutants in the environment, like the persistent organic pollutants, heavy metal pollutants, nanomaterial pollutants, and micro and nanoplastics, etc. And these pollutants display harmful effects on the environmental and human bodies. Some studies show that they have negative effect on the respiratory system, cardiovascular system, and the reproductive system, etc. And today I'll focus on the micro and nanoplastics pollution, which is emerging pollutants attracted greater attention in recent years. And the misproduction and the improper disposal of plastics leads a large amount of plastic waste entering the environment under the action of the photodegradation and the mechanical crushing. The large piece of plastics are decomposed into micro and nanoplastics, where microplastics refers to a particle with size less than 5 millimeter, and nanoplastics refers to a particle with a size less than 1 micron. Since the large piece of plastic degraded into these particles, so their abundance in the environment is increased significantly. And since their particle size is become smaller, so they can be ingested by organisms and cells easily. And in addition, toxic chemicals can be absorbed on these particles and then released to the food chain and then passed right to the human and the environment. And micro and nanoplastics are ubiquitous in the environment. It has been detected in the human blood, and the average concentration can reach 1.6 milligram per millimeter. And humans are exposed to micro and nanoplastics via the ingestion, inhalation, and thermal exposure. When the micro and nanoplastics enter the human body, they may cause harm to humans. Some studies show that they may decrease the heart rate and damage to cells. In order to obtain the sources, distributions, risk behaviors, even the measures that we can take to treat these pollutants, the careful and sensitive analysis is very important. And this figure shows the overview of the analysis process of the microplastics, which involves the sampling, extraction, purification, and detection. As for the detection, chemistry provides a set of identified tools like the microscopy, mass spectrometry, and molecular vibration spectroscopy. And today I will focus on a special identification technique, Raman spectroscopy. Raman spectroscopy is based on inelastic scattering of light. It's akin to a fingerprint of the chemical structure. It allows the identification the chemical composition of samples. similar to SEM when the pixel or the position information provided, the intensity of the characteristic peak can be mapped into the image to visualize the samples and compared with the infrared spectroscopy that has a higher resolution or up to 7 micrometer. And it also has the advantages of the non-destructiveness, wide spectral coverage, low water interference, and narrow spectral bands. But the Hall sensitivity of the Raymond spectroscopy limits its application. And surface enhanced Raymond spectroscopy is a sensitive analytical method developed based on Raymond spectroscopy. When the analysis is close to the surface of the cell substrate, its detection signal can be enhanced by the electromagnetic enhancement or the chemical enhancement. Then the high sensitivity composition analysis can be realized, and in combination with the Raymond mapping, the high resolution visualization also can be achieved. So the research is a promising method in the analysis of the nanoplastics. And later, I will introduce the application of the Raymond and the SIRS in the analysis of micro and nanoplastics. And in this part, I will introduce the application of the normal Raymond spectroscopy in the analysis of the microplastics. And the first example is the detection of the microplastic in the human thrombi. And the thrombi samples were collected from the patients receiving the cardiovascular surgical operations. Because during the formation and the enlargement of the thrombuses can trap the content in the vascular and then become a reservoir of the microparticles. So analyzing the quantity and the type of the microparticles in the thrombus can reflect the accumulation of the microparticles in the main blood vessels. And this figure shows the whole detection process that includes the collection, the sampling and digestion sample with the potassium hydroxide, and then enrichment of the microparticles via the membrane filtration, and then detect the microparticles via the Raymond spectrometer. Consider Raymond spectrometer has a higher resolution, so the particles with a diameter larger than 1 micron has been detected. And these figures given the spectra and the photo of the microparticles detected in the thrombi samples. And we can see using the Raymond spectroscopy, the spectra and the color size and even the surface morphology of these particles can be obtained at the same time. And these particles as the erythrocyte size, this allows it to circulate in the blood system. And this figure shows the characterization and the distribution of these particles in the samples of 26 samples. There are 14 samples have been detected the microparticles, and it also has the microplastics. And they have found a positive association between the particle number and the platelet levels. This is because the increasing the particles in the blood system, they will the correlation between the microparticles and the platelets and the initial thrombus will be increased, and which speeds up the thrombosis. And also this study provides the but this study can't provide the accurate mechanism on the thrombus, but it's supposed that the mechanism for the thrombus may include the involvement of the exogenous factors. And this another sample using the Raymond spectrometer in the biological sample analysis is the analysis of microplastic in the placentas, because the pregnancy and the infancy is the sensitive windows for the environmental exposure. And similar to the last example, it also includes this process that is sampling, digestion, and the enrichment and the detection. And there are 20. This figure is the result, and there are 20 microplastics have been detected in the placentas of the 4 women. Notably, it's only a small portion of the whole placenta that have been detected. It's about 20 grams to a total of 600 grams. So the total number of the entire placenta it will be much higher than this. And we can see this particle size is about 10 micron, and this size is compatible with the possible transmitted in the blood system. And this figure gives the possible width of the entry and transporting of the microplastics to the placenta. And this study sheds light on the exposure, on the level of the human exposure to the microplastics. But the risks need further study. In addition to using the Raymond spectroscopy to analyze the biological samples, it also has been used in the analysis of the environmental samples. And this study using it to analyze the microplastics degraded from the feeding bottles. And it also has been used to analysis of the aging process of the microplastics, where the peak position change and the peak intensity change. We can see that the above studies is analysis the microplastics. And in this part, I will introduce the application of the surface enhanced Raymond spectroscopy in the analysis of the nanoplastics. We know that when the large piece of plastic enters the environment, it will undergo the continuously degradation. So the degradation process of particles will not stop at the micron level. It will be continuously degraded into the nanoplastics. And compared with the microplastics, nanoplastics properties is different. It has a larger specific area and a smaller size. These properties allow it to absorb more pollutants and can ingest it by cells more easily. But the poor sensitivity of the Raymond spectroscopy and the weak intrinsic signal of the nanoplastic making using the normal Raman to analyze nanoplastic is impossible. So the search is maybe a promising method. And the first study to using search to detect the nanoplastics is using the CO nanoparticles as the search substrate. And this study is mixing the nanoplastic solution and the CO nanoparticles together, and then adding the precipitating agent, and then clock the Raman signal. We can see that compared with the normal Raman, the signal was enhanced, and this method limit of detection of this method can reach the 0.34 milligram per millimeter for the nanoplastics with size of 100 nanometer and 500 nanometer. And this study shows that using the search to detect nanoplastic is feasible. To improve the performance of the search method, this study using the claret as the search substrate. And this substrate has a dense grid of the inverted cavities made of gold. These cavities can focus light to form a three-dimensional hotspot, which can enhance the detection signal. And we can see that single particle can be detected with a nanoplastics with size of 360 nanometer. And in combination with the Raman mapping, the distribution of the particles was also obtained, and the particles in the alpine air also detected. It should be noted that the detection process is drops the analysis on the substrate surface and then detected. Before the detection, they need to verify. They need to use the solvent evaporating to concentrate the analysis. It is time consuming. So in order to combine the enrichment process and the detection process, this study using the silver nanovirus membrane and the cell substrate. The detection process is filtration the solution to make the nanoplastics retained on the membrane and then detect it with the Raman spectrometer. And we can see using this method, the about 90% of nanoplastics are retained on the membrane, and the detection of limit can reach 10 to -7 grams per liter. Similar to the last example, in combination with the Raman mapping, the distribution can be obtained. And this method was further improve the performance of the search method. But we can see that this method is complex because it needs to filtration and then detection. And my current work is to use the silver needle as the substrate, and the detection process is immerse the needle in the solution and then take out to detection. And using this needle has the superiority of the simple operation and high sensitivity. We can see that it also can realize the single particle detection. But considering there are the matrix in the blood and the environmental samples is more complex, so the further modification is needed to improve this method's selectivity. To sum up, I have introduced the application of the Raymond search in the micro and nanoplastic analysis. As for the normal Raman, the normal Raman has been used in the analysis of the biological samples and the environmental samples. Based on this data, we can reveal the risks of the microplastic to the human. And the studies on the nanoplastic is at the beginning stage, and the method based on search needs to be continuously improved to meet the detection requirement of the biological samples. That's all. Thank you.
Thank you, Jian. We have time for several questions, 2 or 3. Any question from audience?
Well, thank you, Qing, for your wonderful presentation. It's very comprehensive. So I have a simple question for you. Is that the information is very rich. It's very comprehensive. I'm trying to understand which part is review or which part is your own contribution, if any, so far.
This is my work now, and yeah.
Right.
And,
so good. Go ahead, please.
Oh, okay. And the first part background and using the normal Raman is and this part is the review of the other papers. Okay.
So the last part, the civil needle, is the thing you are trying, right?
Yeah.
Right. Now, yeah, for this part, my understanding is correct or wrong? So what you detect the particle? Is the particle bonded with any kind of biomaterials, or what do we mean by a single particle there?
You mean what this particle is?
Yeah, the single
what?
particle. So can you define what is single particle there? Is that kind of a marker by markers, or just a kind of a nanoparticle without any biomaterial there?
This single particle is the we can see this the optical image. We can see a smaller dispersed particle on the needle surface, and this particle is nanoplastics.
So yeah, so do I understand it correctly? So far, it's not markers from cardiovascular blood. I mean, with cardiovascular disease.
Yeah,
it's just a kind of physical particle, right?
Yeah, because this is I just started my work last month ago.
Sure. I understand.
Yeah.
I understand. It's already very good review. I think very important to start with the comprehensive review, know what's going on, then identify scientific problem to work on. That's no problem at all. So what is your next step you're going to do with this SARS? What are you going to do with this? Which part do you think would be innovative, important enough for your thesis? So is this too early?
6 months work.
Okay.
Plus qualified examination. Yeah, I think the idea I try to answer. Idea is to find a material to attract the biomarker. So the idea here is to see if the needle sensor can with needle sensor, we can see the small size of particle. Then in future, that will be the particle from a blood vessel, if any, and attracted by some biological matter to attract this identified biomarker. I don't know if I say that clearly. So, for example, for the COVID-19, okay, we have used another material to attract the COVID-19 virus on our needle, and we can see the virus. Here is we try to do the similar strategy, but first thing we need to see if we can see a small particle using this needle type sensor. And this was what Jian has done to demonstrate this.
Thank you. I guess eventually you use this needle put in the whole blood, and then to see whether you can catch some biomarkers. Now, there's a question in the chat box that's asking, have you ever tried to measure particle size? If yes, what is the size of particle?
I haven't, but I use this particle with the size of the 500 nanometer is the standard sample.
Okay. Thank you. I have no more questions. Thank you.
Oh, okay, thank you.
Okay. So I think it's time for conclude. So probably I let Raymond to conclude first, and I will follow up.
Okay, thank you. Yeah, Jian. And so thank you. I guess today we have many participants, right? So I hope that so you can well understand more about our research. So as I said at the beginning, so the at least for my talks, for my students' talks, they are work in progress. So I hope that well you have a glance of what we are doing, and then if you think that there are something that we can collaborate, then please don't hesitate to talk to us, because we are mathematicians. We do not know exactly what is needed in practice. So then it's very important that we talk to people exactly what is required. Otherwise, then we are just making things that are unrealistic. So that's why it's very important that we give talks here. So I well, maybe I stop here, and then I give it back to Jian.
Okay, thank you, Raymond. So I think the two talks from my group, we try to develop two generic methods. One is for doing the dilution or concentration using the microfluidic system. Another is to do the measurement in the micro and the nanoparticle, because we all know with the cardiovascular disease, we may have some debris during the stroke, and we try to collect this and see if we can see something. So I think we are in progress, and these four talks are quite fundamental. So if any person who are interested by the application of this 2 by 4 generic numerical method and experimental method, we are open for collaboration. And we can directly measure in the blood and urine and saliva, all these kind of human body fluid, and we are open for collaboration. And the two students in my group, they are in first years. This will stay here at least for 3.5 years, and so we have time to collaborate. So, any other comments in the audience? There is one question in the chat board. Where? In the particle size?
Mm-hmm.
Yeah, as Jian has demonstrated for the moment, I think it's around 1 micron, the particle size. I think typically it's larger than what we can find in the accident, cardiovascular accident incident. But the problem is how to extract, because when you extract the blood, then you may not meet this particle. Another question? What's the limit of detection of this method? I hope, yeah, the limit of this method. So basically, for the MAMON, the surface enhanced Raman spectroscopy, for some classic liquid, the amplification is around 100,000 times. And for this standard liquid, our new method with needle can go to up to 10 million times of amplification maximum. So 10 to 100 times more sensitive compared to today's technology using chips, semiconductor chips, and nanoparticle of gold and silver. But it's not, the results, I say, is not on the blood, it's on the other standard standard liquid, such as rhodamine or other calibration liquid. Because the biological sample is more complex. We have some experiences for the COVID-19. So we have successfully developed chemical product that attract the COVID-19 virus to amplify the signal. And here we are still working on the cardiovascular part. I don't know if it's clear for my question. Okay. Okay. Any other question and comments? So if not, I would like to thank all of you, because I see we have 72 persons, so it's quite a successful seminar.
Yeah. Yes.
Okay. Okay. So thank you very much, and see you next time. Thank you.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Thank you.
Bye-bye.
Bye-bye. Thank you. Bye-bye. Bye-bye. Thank you.